Multinomial distribution. Multinomial distribution is a generalization of binomial distribution to model experiments with more than two possible outcomes. That is, initially we learned about Bernoulli distribution, then about binomial distribution, and now you are learning about multinomial distribution. Let's understand what is the difference between these three. In case of Bernoulli, we kept two conditions. The first condition was that there will only be one trial, and the second condition was that the outcome will always be binary. That is, only two outcomes will be possible, namely success and failure. Coming to binomial, we again said outcome will be binary, which is only success and failure is possible, but you can have n different trials of the experiment. What is the case of multinomial? Here we are saying that you can have n different trials of the experiment and you can have k different outcomes possible and not just the success and failure. So if you have only one trial and binary experiment, then use Bernoulli. If you have n trials of a binary experiment, use binomial. If you have n trials and the experiment is not binary, but you have a lot of options, then you use multinomial distribution. Let us understand multinomial in more detail. It goes like this. You have k different possible outcomes and each of those outcomes have a probability pi. Previously we said that in case of success you have a probability p and in case of failure you have a probability 1 minus p. This is because it was a binary experiment in case of Bernoulli or binomial. Here it is not binary, so it's not just p and 1 minus p. You have p1, p2, p3 so on up to pk because you have k different experiments, right? So this is the case with multinomial. Let us understand like this. Let us say first try. This is your first try in which you can take any of these possible outcomes. In the second trial, you can again take any of these possible outcomes. Third trial, any of these possible outcomes and so on. So let us say you did some experiment. Maybe in the first trial, this one came as the outcome. In the second trial, this one came as the outcome. In the third trial, maybe let's say this one came as the outcome and so on. So this is how it works. So let us first define the parameters. What are the parameters here? First parameter is n, which is the number of trials, right? Number of trials. This is your first parameter. Second parameter is pi. What is pi? It is the probability of outcome in each trial. That is probability of outcome in each trial. Let us say ith trial. Okay. In ith trial, what is the probability of outcome? So probability is pi. One condition that you have to see here is because pi is probability, your summation over all the pi's, that is, if you have k different outcomes possible, then your summation over all the k, that is I equal to 1 to k pi, this should always be equal to 1. Why? Because this is your probability. If I am saying that I have a total of 4 different possible outcomes, outcome can be 1. Let us say I am rolling a dice. In that case, if I am rolling a die, I will have 6 different outcomes. 1, 2, 3, 4, 5 and 6, right? A die has 6 faces and they will be numbered from 1 to 6. If my probability, let us say this is not a fair die, which means the probability of each of the faces falling is different. In that case, I will say my probability of, let's say, getting 1, maybe this is 0.1. Probability of getting 2, maybe this is 0.2. This is 0.1. This is 0.2. This is 0.2 and so on. But what is the condition? This should all sum up to 1. So this is 0.2, 0.4, 0.6, 0.7, 0.8. Again, it will be 0.2. So if you sum all these, you will get 1. That is the basic rule with probability, because what all are the chances? If you sum all those, you should get 1. Let us understand the probability mass function PMF for a multinomial distribution. We already saw the probability mass function for Bernoulli first, then we understood binomial, and now we are looking at multinomial distribution. So let us understand the probability mass function PMF. let us write it as P of, here x, each of the x you have to consider, not just one x, because you have x1, x2, x3 up to xk. K different possibilities are there. So probability of x1 equal to x1, x2 equal to x2 up to xk equal to xk. This is what your probability mass function would determine. That is, this is trying to identify the probability of one particular occurrence. What will happen in one particular occurrence? Each of your k different possible outcomes will take one value. So let's say your first value has x1, second is x2, up to kth one is xk. So this probability is what you're trying to find. How can you identify this probability? For each of the outcome, there is a probability. So let us say the first one occurred x1 times. Okay. So we are considering that, let's say you did it many times. And out of these n trials, you did a total of n trials. Out of these n trials, let us say x1 times the first one occurred. Okay. X1 occurrences are of the first type. Then let's say x2 occurrences are of the second type. X3 occurrences are of the third type, and so on. Let us say this is the case. In this case, what will happen? If you sum all the x's, that is I equal to 1 to k. Why is it 1 to k? Because there are k different possibilities of the outcome. So if I do I equal to 1 to k xi, that is the total number of possibilities, that should always sum up to 1. So one condition is that all the counts should sum up to n, and the other condition is all the probabilities, they should sum up to 1. These two conditions we are having. Under these conditions, I'll write an equation and you tell me whether it is right or wrong. Do you see it logically right or not? I'm saying that there are x1 different occurrences of the first choice, which means considering that P1 is the probability of first option occurring, that is the first outcome. I'm having k different outcomes, 1, 2 up to k. K different outcomes are possible. So let me erase this and write on top. That will be more clear. So my probability mass function, I will write it as probability of x1 equal to x1, x2 equal to x2, so on up to xk equal to xk. Okay, I'm simply writing this as p so that I get more space. Okay, you understand that it's a total expansion. I'm simply writing as p of x. This is equal to, I know that there are x1 different occurrences of first choice, x2 different occurrences of second choice, in the sense second outcome. I have different outcomes, 1, 2, 3 up to k different outcomes are possible for this experiment. So outcome 1 occurred x1 times, outcome 2 occurred x2 times, outcome 3 occurred x3 times, and so on. So outcome k occurred xk times. In this case, the sum of all outcomes, that is I equal to 1 to k xi, this should be equal to n, because total number of trials is n. So if x1 occurred, 1 occurred x1 times, second outcome occurred x2 times, and so on up to kth outcome occurred xk times, then if I sum up all the occurrences, the total should be n. And the second condition is, if I sum up all the probabilities, that should be 1. Considering this, I know that the probability of the first outcome occurring is P1. The probability of second outcome occurring is P2. Probability of third outcome occurring is P3, and so on. Given this, can I write the total probability as probability P1, let's say P1 raised to x1, because x1 times P1 occurred, right? So that will be P1 into P1 into P1 into so on in case of probability. So first occurrence, first outcome that I am handling here as P1 raised to x1. Second outcome, P2 occurred x1, x2 times. So P2 raised to x2. Third outcome, P3 occurred x3 times. So p3 raised to x3, so on up to pk raised to xk. Do you think this has covered all the possibilities? Just remember what we did in case of binomial distribution and try to connect it to multinomial distribution. What was the missing term there? In case of binomial, we had seen that we had to see all the combinations. Same case here. You have to see all the combinations in which this can occur. That is, x1 times first outcome occurred, x2 times second outcome occurred, x3 times third outcome occurred, but this can occur in different combinations. That is, maybe in the first trial x1 occurred, first outcome occurred. In the second trial, again first outcome occurred, say, again first outcome, then few second outcomes, then few third outcomes, and so on. It can also happen like first time outcome occurred, then few second outcomes, then few third outcomes, so on. We are only taking care of count here. So we also have to take care of the occurrences, that is at what position which outcome is occurring. So how do you consider all those? By considering the number of ways in which it can permute. So here you have a total of n different trials. So the ways of arranging n different items. How can you arrange n different items? Total is n factorial. But out of these, there will be a lot of common ones which you have to take care of. So out of n factorial is the total number of ways in which you can arrange n items. But out of these n items, you know that x1 items are common. Similarly, x2 items are common. x3 items are common, right? These many items are of same type. So if I have, let's say, 3 items of the type x3 and I keep 3 items here, instead if I keep this item here or this item here, these are all the same arrangement, because all those 3 items are one and the same. Whether you keep the first one on the left or the last one on the left, no one is going to notice. So here you know that out of the n items, x1 items are of same type, x2 items are of same type, x3 items are of same type. In that case, what you have to do, you have to handle that many cases specifically. So out of all the n factorial combinations, x1 factorial combinations represent items of the same type. So you have to divide that much. Similarly, x2 factorial are of the same type up to xk factorial. So this is the total number of ways in which you can arrange these. So now you have the actual PMF, that is probability mass function of a multinomial distribution. It includes 2 terms. The first term, which is n factorial by x1 factorial, x2 factorial, x3 factorial up to xk factorial. This term denotes the number of ways in which you can arrange all these occurrences. And the other terms, p1 power x1, this handles all the occurrences of first outcome. That is x1 times first outcome is occurring, which means with each occurrence with a probability p1. So p1 raised to x1 handles all the occurrences of outcome 1. Similarly, p2 power x2 handles all the occurrences of outcome 2, outcome 3, outcome 4, so on up to outcome k. So this probability mass function it handles all the outcomes and all the combinations in which those outcomes can occur. So this is the probability mass function for a multinomial distribution. So I hope you understood it logically and also mathematically here. So the next thing is understanding expectation and variance. What is the expectation? So again here, because it is multinomial distribution, you have to consider x is equal to, instead of simply taking expectation of x, you can only take expectation of one particular xi. That is, you have to take expectation of one outcome. See, previously you were taking expectation of that variable. You have to consider the expectation of the ith outcome, which will be, see, in case of our binomial distribution, we said expectation can be written as n into p, where p is the probability of success and n is the total number of trials. In case of binomial, this was where This was our expectation. In case of multinomial, I'm not deriving the expectation because instead of derivation, it's better you just understand the this logically. So the expectation in case of multinomial, this is n into pi, where n is the number of total trials and pi is the probability of ith outcome occurring. So the reason I'm not deriving is it's easier to connect logically with binomial, and derivation is going to be larger if you do it from multinomial distribution. So in case of expectation, in binomial, it was NP was the expectation, where P is the probability of success. Here you have K different outcomes. So for each outcome, you have to find expectation separately. For the ith outcome, expectation can be written as N into Pi, where Pi is the probability of ith outcome and N is the total number of trials. And what about variance? Variance also you have to consider for each of the outcomes separately. In case of multinomial, in binomial we had seen variance was NP into 1 minus P. This was the variance in case of binomial distribution. In case of multinomial, the same thing occurs as N into Pi into 1 minus Pi. So you can directly relate these results from binomial distribution.